Okay, this is part 7b97z33, line 22, 7b97z33, Photonic-Crystal Hollow Core Laser Fibers UFO Core Engine Communication Signals, 5G Wow Seti. That's the alien radio signal there. Okay, this video is about the hollow core laser fibers with signals, gases, liquid argon, and plasma going up inside of them for the UFO space communications device found in line 22 of the WOW data. I was working on it August 21st, 2013. Today, September 14th, 2013. So this is from previous video was line 22, 7b97z32. Crystal photonic, crystal fibers, lasers, Bragg, diffraction, UFO core engine, communication signals, 5G Wow Seti. Photonic crystal fiber was the key word, and the quote from wiki. Actually, sorry, I forgot to write that down. Construction. Generally, such fibers are constructed by the same methods as other optical fibers. First, one constructs a preform on the scale of centimeters in size, and then heats the preform and draws it down to a much smaller diameter, often nearly as small as a human hair, shrinking the preform cross-section but usually maintaining the same features. In this way, kilometers of fiber can be produced from a single preform. The most common method involves stacking, although drilling milling was used to produce the first aperiodic designs. This formed the subsequent basis for producing the first soft glass and polymer structured fibers. Most photonic crystal fibers have been fabricated in silica glass, but other glasses have also been used to obtain particular optical properties such as a high optical non-linearity. There's also a growing interest in making them from polymer, where a wide variety of structures have been explored, including graded index structures, ring structured fibers, and hollow core fibers. These polymer fibers have been termed MPOF, short for microstructured polymer optical fibers, Van Elgekenborg, 2001. The combination of a polymer and a genide glass was used by Temelgren, AL 2002, for 10.6 wavelengths, where silica is not transparent. Modes of operation. Photonic crystal fibers can be divided into two modes of operation according to their mechanism for confinement. Those with a solid core, or a core with a higher average index than the microstructured cladding, can operate on the same index guiding principle as conventional optical fiber. However, they can have a much higher refractive index contrast between core and cladding, and therefore can have much stronger confinement for applications in nonlinear optical devices. Polarization, maintaining fibers, or they can also be made with much lower effective index contrast. Alternatively, one can create a photonic bandgap fiber in which the light is confined by a photonic bandgap created by microstructured cladding, such as a bandgap properly designed can confine light in a lower index core and even a hollow air core. Bandgap fibers with hollow cores can potentially circumvent limits imposed by available materials, for example, to create fibers that guide light in wavelengths for which transparent materials are not available, because the light is primarily in the air, not in the solid materials. Another potential advantage of a hollow core is that one can dynamically introduce materials into the core, such as a gas that is to be analyzed for the presence of some substance. PCF can also be modified by coating the holes with sol gels of similar or different index material to enhance its transmittance of the light. So we see also photonic crystal, optical medium, fiber optics, gradient index optics, optical communication, fiber Bragg grading, leaky mode, subwavelength-diameter optical fiber, and the keyword I'm going to look up is subwavelength-diameter optical fiber in our next video. Thanks for watching.